Are there some numbers that are used more frequently in societies than others?
There are numbers that appear to be used more frequently by some cultures than by others. For example, according to The Secret Life of Numbers by Golan Levin, al. 2002, certain numbers, such as 212, 911, 1040, 1492, 1776, or 90,210, occur more frequently. Because they are used to identify such entities as phone numbers, zip codes, tax forms, computer chips, famous dates, or even television programs that figure conspicuously in Western culture. Picking the powers of 10 also reflects the standard base 10 numbering system used in the West. Numbers such American Samoa 1 2 3 4 5 456, or 9,999 are used because they are easy to remember.
Are there some numbers that are used more frequently in societies than others?
There are numbers that appear to be used more frequently by some cultures than by others. For example, according to The Secret Life of Numbers by Golan Levin, al. 2002, certain numbers, such as 212, 911, 1040, 1492, 1776, or 90,210, occur more frequently. Because they are used to identify such entities as phone numbers, zip codes, tax forms, computer chips, famous dates, or even television programs that figure conspicuously in Western culture. Picking the powers of 10 also reflects the standard base 10 numbering system used in the West. Numbers such American Samoa 1 2 3 4 5 456, or 9,999 are used because they are easy to remember.
What is sociology?
Sociology is the study and classification of human societies. It delves into the relationships among peoples mostly within, but also outside, each culture. Sociology studies are based on the idea that behavior of peoples is influenced by social, political, occupational, and intellectual groupings. It is also based on the immediate and particular settings in which individuals reside.
What is sociology?
Sociology is the study and classification of human societies. It delves into the relationships among peoples mostly within, but also outside, each culture. Sociology studies are based on the idea that behavior of peoples is influenced by social, political, occupational, and intellectual groupings. It is also based on the immediate and particular settings in which individuals reside.
What was the original use of Stonehenge?
One of the most famous ancient stone complexes is England's Stonehenge. An impressive engineering and mathematical feat. Several groups of local inhabitants constructed this collection of large and small stones grouped in 4 concentric circles, 2 of which are created by paired upright stones bearing huge capstones between 2950 and 1600 BCE. Based on how the stones line up with various astronomical events, historians believe the entire structure represents a huge, literally monumental, calendar. For example, various stones align with the moon, the full moon's extreme positions on the horizon are marked at Stonehenge, and with the sun, including the summer solstice. It is also thought that the complex served as a place in which ancient rites and rituals were performed on significant days of the year. And it was all built without the help of computers.
What is sociology?
Sociology is the study and classification of human societies. It delves into the relationships among peoples mostly within, but also outside, each culture. Sociology studies are based on the idea that behavior of peoples is influenced by social, political, occupational, and intellectual groupings. It is also based on the immediate and particular settings in which individuals reside.
When was a mechanical calculating device first used for the American census?
When government officials estimated that the 1890 census would have to handle the data from more than 62 million Americans, there was a slight panic. After all, the existing system was slow and expensive. Using tally marks in small squares on rolls of paper, which were then added together by hand. One estimate determined that such an endeavor would take about a decade to complete, which would be just in time to start the process all over again for the 1900 census. In desperation, a competition was set up to invent a device that could easily count the 1890 U.S. Census. Thus, in the 1880s, American inventor Herman Hall Erith, 1860 to 1929, who is also known as the father of modern automatic computation, presented his competition-winning idea. He used jackards punched cards to represent the population data. Then read and collated the information with an automatic machine. With his automatic tabulating machine and automatic electrical tabulating device, Hollerith would put each individual's data on a card. With a large number of clock-like counters, he would then accumulate the results. From there, he would use switches so the operators could instruct the machine to examine each card based on a certain characteristic, such as marital status, number of children, profession, and so on. It became the first such machine to read, process, and store information. The machine's usefulness did not end there, though. Eventually, Hollerith's device became useful for a wide variety of statistical applications. Certain techniques used in the automatic tabulating machine were also significant, helping in the eventual development of the digital computer. Hollerith's company would also eventually become well known, becoming International Business Machines, or IBM, in 1924.
Who was Vitruvius?
Marcus Vitruvius Pollio, c. 1st century BCE, was a Roman writer, architect, and engineer. He was the author of De Architectura Libri de Cm, known today as the 10 Books of Architecture. This Latin treatise, dedicated to Octavian, the heir and adopted son of Julius Caesar, was written around 27 BCE. For more about Octavian, see Mathematics Throughout History. Possibly the first works published about architecture, the books entailed a compilation of architectural ideas of Vitruvius's day and covered the following 10 subjects: principles of architecture, history of architecture and architectural materials, Ionic temples, Doric and Corinthian temples, public buildings, theaters, music, baths and harbors, town and country houses, interior decoration, water supply, dials and clocks, and mechanical engineering with military applications. Specifically, the topics included such forward-thinking ideas as the manufacture of building materials and dyes, material science, machines for heating water for public baths, chemical engineering, amplification in amphitheaters, acoustical engineering, and the design of roads and bridges, civil engineering. De Architectura was wildly successful, and Vitruvius's architectural advice was followed for centuries. But because Vitruvius's books were passed down through the ages, they were copied by various people, especially throughout the Middle Ages. Many medieval engineers added information to the texts, treating the books as handbooks, not documents to be preserved. In the end, historians have had to winnow away the added sections to find the true writings of Vitruvius.
What problems were computers originally invented to solve?
Originally, computers were invented to solve numerical problems. Now, very few mathematicians, scientists, computer scientists, and engineers can imagine a world without computers. Advances in technology have also led to an increase in accuracy, the number of problems that can be solved, and the speed in solving those problems a far cry from the earliest computers.
What is the music of the spheres?
Not only was the Greek mathematician and philosopher Pythagoras of Samos, c. 582 c. 507 BCE, credited as the first to prove the Pythagorean theorem. He also discovered the music of the spheres. He found that the pitch of a musical note depends on the length of the string producing the sound, enabling him to develop intervals of the musical scale with simple numerical ratios. When a stringed instrument is played, if the musician puts pressure halfway along the string's length, he or she produces a note that is 1 octave above the string's note. In other words, the same quality of sound but at a higher pitch. Octaves increase by 1 step each time a string vibrates at twice the frequency of the previous note. This is expressed mathematically as a frequency ratio of 1:2, string octave. Pythagoras recognized other ratios, too, such as the perfect fifth ratio 2:3, and the perfect fourth, 3:4, thus developing the mathematical basics of musical harmony. Pythagoras took music and mathematics a bit further. Believing that the musical octave was the simplest and most profound expression of the relationship between spirit and matter. For more about Pythagoras, see below and History of Mathematics. He also taught that each of the known planets produced a particular note, generated by its motion, according to the planet's distance from the Earth. Calling this musica mundana, or the music of the spheres, it was music no one could really hear. He and his followers, called the Pythagoreans, further used music to heal the body and to elevate the soul. Yet they believed earthly music was just a faint echo of the universal notes. Although today it may seem more magic than hard science and mathematics, maybe Pythagoras was right. After all, many researchers believe music does have the capacity to heal a person under certain circumstances.
What is the definition of a modern computer in today's sense of the word?
In general, and simply put, a computer is a machine that performs a series of mathematical calculations or logic operations automatically. Computer specialists often divide computers into two types. An analog computer operates on continuously varying data, a digital computer performs operations on discrete data. The majority of today's computers easily process information much faster than any human. The response, output, of a computer depends on the data input, of the user, usually controlled by a computer program. A computer also can perform a large number of complex operations, and can process, store, and retrieve data without human interference. There is a great deal of overlap for the word computer. In a more archaic sense, a computer is called an electronic computer, or computing machine or device. The more common expressions include data processors or information processing systems. But remember, there is a definite difference between a computer and a calculating machine. A computer is able to store a computer program that allows the machine to repeat operations and make logic decisions.
What is a Vedic square?
Historically, in order for Islamic artisans to create a variety of geometric patterns, a Vedic square was often used. The Vedic is an ancient religion associated with India. For more information, see below. These squares generate patterns by the selection of number sequences and angles. Each square is made by taking a multiplication table and reducing all the numbers to single digits. For example, if a number in the table was 81, it would be reduced by adding 8 plus 1, or 9. Then, to get a design, for example, a certain line of numbers would be chosen, such as connecting all the number 5s. And by using a fixed angle of rotation with the lines, various designs were drawn. These number patterns are distinctively Islamic and helped create many of the famous traditional Islamic geometric designs seen today.
What is a microprocessor?
A microprocessor is a silicon chip that contains a CPU, or central processing unit, which is normally located on the main circuit board in a computer. In the world of personal computers, the terms microprocessor and CPU are often used interchangeably. These chips, or integrated circuits, are small, thin pieces of silicon onto which the transistors making up the microprocessor have been etched. The microprocessor is the heart of any normal computer, from desktops and laptop machines to a larger server. They have many uses. For example, they control the logic of almost all familiar digital devices, from microwaves and clock radios to fuel injection systems for automobiles.
How are the principles of ratio, proportion, and symmetry applied to architecture?
The definition of a ratio is a comparison by division of two quantities expressed as the same unit measurement. For example, a building that is 200 feet wide and 100 feet tall has a ratio of 2:1, 200:100, between its width and height. It is also seen as the fraction 1/2. Such a relationship was understood as far back as ancient Greece and Rome, when people used mathematics to give structure and aesthetics to buildings. This is especially important in architecture, in which building design is based on complex mathematical ratios. Proportion is an equation stating that two ratios are equal. Every proportion has four terms, with the first and fourth terms being the extremes. The second and third terms are called the means. In each proportion, the product of the means equals the product of the extremes. The Greeks and Romans often used proportions in their buildings and other structural designs. The Roman architect Vitruvius was also instrumental in praising the virtues of proportion and symmetry in architecture. For more about Vitruvius, see above. During the Renaissance, architects applied proportion and other mathematical formulas to produce aesthetically pleasing buildings, beauty that still holds true today. Although there are other types of symmetry, the most common is line symmetry, in which a line divides an object, line, or other structure into two equal halves. An example in nature would be the wings of a butterfly. If a line of symmetry is drawn, each point on one side of the line has a corresponding point on the opposite side of the line. If you connect these 2 points, the line is perpendicular to the line of symmetry. There is a more mathematical way of defining symmetry. 2 points are symmetric about a line if the line is the perpendicular bisector of the segment joining the 2 points. Symmetry was used by ancient and modern architects to maintain visual and sometimes structural balance of a building or structure.
What type of number system is used by modern computers?
Modern computers use the binary system, a system that represents information using sequences of zeros and ones. It is based on powers of 2, unlike our decimal system based on powers of 10. This is because in the binary system, another number place is added every time another power of 2 is reached. For example, 2, 4, 8, and so on, in the decimal system. Another place is added every time a power of 10 is reached, for example, 10, 100, 1000, and so on. Computers use this simple number system primarily because binary information is easy to store. A computer's CPU, central processing unit, and memory are made up of millions of switches that are either off or on. The symbols 0 and 1 represent those switches, respectively, and are used in the calculations and programs. The two numbers are simple to work with mathematically within the computer. When a person enters a calculation in decimal form, the computer converts it to binary, solves it, and then translates that answer back to decimal form.
What is the historical significance of the golden ratio?
It is thought that over the centuries many architects and painters used the golden ratio in their works. Some historians believe that the Great Pyramid of Cheops contains the golden ratio. The ancient Greeks knew about the golden ratio from their works in geometry, but they never truly believed it was as important as numbers such as pi. Many works of art in the Renaissance are thought to have used the golden ratio within paintings and sculptures, although it may have been subconsciously incorporated into their compositions. In 1509 Luca Pacioli published the work Divina Proportion, which explored the mathematics of the golden ratio, along with its use in architectural design. Of course, humans aren't the only ones who practice the golden ratio. It is also seen in nature as the result of the dynamics of some systems. For example, the spacing of sunflower seeds and even the shape of the Chambered nautilus shell are often claimed to be related to the golden ratio.
How did early painters integrate mathematics and painting?
Early painters had a problem: how to represent the three-dimensional world on a two-dimensional canvas. Or, how to give paintings depth and perspective. Although perspective does follow mathematical guidelines, many early painters were able to incorporate perspective, or depth perception, intuitively. The idea of perspective flourished around the time of the ancient Greeks, who used a form of perspective to design certain architectural structures and even theatrical stage settings. But it is unclear whether they actually understood the mathematics behind perspective. One of the first to create the impression of depth by using certain rules was Italian painter, sculptor, and architect Giotto di Bondone, c. 1267–1337. But those rules were of his own devising and were probably not based on mathematics. Whatever the case, he clearly worked out a way to represent depth in space. And he came close to understanding linear perspective. But it took until the Renaissance before painters explored the science behind perspective. In the early 1400s, sculptor Filippo Brunelleschi, 1377–1446, made the first correct formulation of linear perspective using mirrors. He understood that there was a single vanishing point to which all parallel lines in a plane, or on his canvas, converge. He also understood scales, calculating the relationship between the actual length of an object and its length in the picture, depending on its distance in the painting. Writer and mathematician Leone Battista Alberti, 1404–1472, was the first person to write the rules of perspective in 1435. Using the principles of geometry and the science of optics. By 1450, artist and mathematician Piero della Francesca, 1412–1492, had written an even more extensive mathematical work on perspective, including concepts of art, arithmetic, algebra, and geometry. The writings of mathematician Luca Pacioli, c. 1447–c. 1517, or Friar Luca dal Borgo, who was also known as the father of accounting, see below, delved more into perspective, including in his book De Divina Proportion, which relied heavily on Francesca's work. The illustrations in Pacioli's book were done by none other than the famous scientist, painter, and Renaissance figure Leonardo da Vinci, 1452–1519, who was himself a great contributor to the study of perspective. Pacioli was one of da Vinci's teachers, and he instructed the eventual great master a good deal about proportion and perspective.
What is perspective?
In painting and photography, perspective gives an image depth, allowing a person to perceive three dimensions in a two-dimensional picture. In art, this can be achieved using certain tools of the trade. For example, the horizon line is the eye level of the artist and viewer. By raising and lowering the viewpoint, it enables the viewer to see more or less of the horizontal plane that lies between the viewer and the horizon. The vanishing point is a point on the horizon line at which parallel lines seem to meet. The classic example is how train tracks seem to come together in the distance. The horizontal baseline is parallel to the horizon line and represents the base of the picture plane. The vanishing point is on the horizon line and is directly opposite, or in front, of the viewer. All of these points, lines, and angles and other ways of bringing depth into a painting are based on concepts in mathematics.
How is geometry used to create Islamic patterns?
Many of the intricate patterns on Islamic architecture, structures, walkways, and fabric incorporate geometry in the construction of the design. From simple shapes, Islamic designs evolved into complex geometric shapes involving a high degree of mathematical symmetry. One of the best places to see such work is in the Alhambra Palace, a Moorish structure in Granada, Spain, built in the 15th century. Some Islamic designs were drawn by eye to be aesthetically pleasing. Others involved collaborations between mathematicians and artists. For example, mathematician and astronomer Abu al-Wafa, 940 to 998 CE, born in today's Iran, worked with artisans in the 10th century, helping to design the ornamental patterns in wood, tile, fabric, and other materials. He discussed such mathematical concepts as constructing a perpendicular at the endpoint of a line segment, constructing a regular polygon, dividing segments into equal parts, and even the bisection of angles. Abu al-Wafa's teachings, and those of others like him, eventually led artisans to design the many intricate patterns seen in Islamic art today.
Why did the Egyptians choose the pyramid form?
Historians know that the Egyptian sun god, with its rays reaching for the sun, was represented by pyramid-shaped stones, or benbens. And because the Egyptians worshipped the sun as their chief god, the pyramids are thought to be huge renditions of the benbens. After a pharaoh died, the pyramids would be symbolic of the pharaoh ascending the sun's rays to join his sun god. Some historians also believe that the pyramids may have had some, still hidden, numerical significance. In particular, some believe the ratio of the pyramid's perimeter to its height times 2, or p/2xh, gives a close approximation to the value of pi. Another claim is that the slopes of the pyramid sides were also expressions of pi.
Who built the first mechanical binary computer?
German civil engineer Konrad Zuse, 1910 to 1995, built the Z1, often thought of as the first mechanical binary computer in his parents' living room around 1938. His goal was to build a machine that would perform the lengthy and tedious calculations needed to design building structures. His computer's design stored intermediate results in its memory and performed sequences of arithmetic operations that he programmed on punched paper tape. He initially used old movie film. This machine led to the Z3 in 1941. Considered by some to be the first large-scale, fully functional automatic digital computer, the computer used a binary number system.
What were some highlights in the development of modern computers?
The first general-purpose analog computer was designed in 1930 by American scientist Vannevar Bush. 1890 to 1974, who built a mechanically operated device called a differential analyzer. The first semi-electronic digital computing device was built by mathematician and physicist John Vincent Atanasoff. 1903 to 1995, and one of his graduate students, Clifford E. Berry, 1918 to 1963, between 1937 and 1942. It was created primarily to solve large systems of simultaneous linear equations. It is interesting to note that Atanasoff's computer was overshadowed by the electronic numerical integrator and computer ENIAC, see below, which was once credited as the first computer. In 1973, however, a federal judge recognized Atanasoff's work and voided Sperry-Rand's patent on the ENIAC, saying it had been derived from Atanasoff's invention. Today, Atanasoff and Berry get the credit. The Harvard Mark I, or the automatic sequence-controlled calculator, was built between 1939 and 1944 by American computer scientist Howard H. Aiken, 1900 to 1973. And his team. It is thought of as the first large-scale automatic digital computer. But there are disagreements about this, with some historians believing that German engineer Konrad Zuse's Z3, see above, was the first such machine. Other early computers were the ENIAC 1 and the UNIVAC. The ENIAC, electronic numerical integrator and calculator, was completed in 1946 at the University of Pennsylvania. It used thousands of vacuum tubes until 1973. It was thought of as the first semi-electronic digital computer. That credit was subsequently given to Atanasoff and Berry, see above. The UNIVAC, Universal Automatic Computer, was built in 1951 and was the first computer to handle both numeric and alphabetic data. It also was the first commercially available computer. The third-generation integrated circuit machines were used primarily during the mid-1960s and 1970s, making the computers smaller, faster, close to 1,000,000 operations per second, and far more reliable. The first commercial microprocessor was the Intel 4004, which appeared in 1971. It could only add and subtract, and it was used to power one of the first portable electronic calculators. The real push in microprocessors came during the late 1970s to 1990s, allowing for increasingly smaller and more powerful computers. For example, in 1974 the Intel 8080 processor had a clock speed of 2 MHz. By 2004 the Pentium 4, Prescott, had a clock speed of 3.6 GHz. Computers that use microprocessors include the personal computer and personal digital assistant, PDA. The computer industry has continued rapid growth, mainly thanks to the increased performance of advanced microprocessors.
Who was M. C. Escher?
Moritz Cornelius Escher, 1898 to 1972. Was a Dutch painter famous for his mixing of art and mathematical concepts. He had no formal math training past secondary school, but he was, and still is, admired by mathematicians for his amazing visualizations of mathematical principles. Escher's interest in mathematical patterns began around 1936, after viewing the Alhambra Palace's collection of Islamic art, see above. He was fascinated with structures represented in plane and projective geometry both. Euclidean and non-Euclidean geometry. For more information, see geometry and trigonometry. Not only using the geometry of space, but also the logic of space. For example, he used the idea of tessellations, or arrangements of closed shapes, usually polygons or similar regular shapes, like those used on a tiled walkway, that cover the entire plane without overlaps or gaps. Not only did he use regular tessellation shapes, but also irregular ones, making the shapes change and interact with each other. He also made many of his amazing patterns by taking a basic pattern and either distorting it and/ or applying what geometers call reflections, translations, and rotations. For many other mathematical patterns, he used regular solids, Platonic solids, and visual aspects of topology in his work. For more about Platonic solids, see geometry and trigonometry.
Are there some numbers that are used more frequently in societies than others?
There are numbers that appear to be used more frequently by some cultures than by others. For example, according to The Secret Life of Numbers by Golan Levin, al. 2002, certain numbers, such as 212, 911, 1040, 1492, 1776, or 90,210, occur more frequently. because they are used to identify such entities as phone numbers, zip codes, tax forms, computer chips, famous dates, or even television programs that figure conspicuously in Western culture. Picking the powers of 10 also reflects the standard base 10 numbering system used in the West. Numbers such American Samoa 1 2 3 4 5 456, or 9999 are used because they are easy to remember.
What is the golden ratio?
The golden ratio, also known as extreme and mean ratio, golden section, golden mean, or divine proportion, is a number that has many interesting properties. It is associated with the balance between symmetry and asymmetry used in art and design. Two quantities are said to be in the golden ratio if the whole is to the larger as the larger is to the smaller. Euclid expressed it as, a straight line is said to have been cut in extreme and mean ratio when, as the whole line is to the greater segment, so is the greater to the less. This is seen in the accompanying illustration, in which for two segments A and B, the entire line is to the A segment as A is to the B segment.
What is the difference between a mini-computer and a microcomputer?
The term mini-computer is not used much today. It is considered to be the type of computer built mainly from about 1963 to 1987, and refers to the mini mainframe computers that were not large enough to be called mainframes but were large enough to take up the space of a small closet. These computers were once popular in small businesses that could not afford the money or space for a mainframe computer. They were much less powerful than a mainframe and were limited in hardware and software. And they were built using what was called low integration logic integrated circuits. Eventually, they were overtaken by microcomputers built around the microprocessor. The microcomputer was a later development in computing. It was developed as a general-purpose computer designed to be operated by one person at a time. The single-chip microcomputer, complete with microprocessor, was, in many respects, a landmark development in computer technology, resulting in the commercialization of the personal computer. This is because computers became smaller and less expensive, and the design made parts easier to replace.
In what ways does mathematics apply to music?
There are many ways in which mathematics applies to music, from harmonics to the concept of octaves and scales. There is a most interesting connection in that both music and mathematics are experienced as pure objects of the brain, and both have meaning outside of the brain only through artificial connections. For example, there is a mathematical reason why Certain note combinations sound harmonious to most people. One good example is a violin string. When it is plucked, the string vibrates back and forth, creating mechanical energy that travels through the air as wave patterns. The number of times the waves reach a person's ear is called the frequency, which is measured in hertz, or cycles per second. If more waves are heard within a certain time period, the note's pitch sounds higher. Chords sound harmonious to us because of waves and ratios. For example, take the C major chord, in which the note middle C is 261.6 Hz. The note E is 329.6 Hz, and the note G is 392.0 Hz. The ratio of E to C is about 5/4, or every fifth frequency wave of E matches with every fourth wave of C. The ratio of G to E is also about 5/4, and the ratio of G to C is about 3/2. Because the notes' frequencies match with the other notes' frequencies, they all sound harmonious to a person's ear. It is interesting to note that none of the ratios for the familiar Western-style scale are truly exact, but rather are approximations. This is because when this scale was put together, the creators wanted to make the notes go up in equal intervals and the ratios to be in tune. The only way to do this was to compromise and use inexact ratios.
What are the modern connections between architecture and mathematics?
The foundations of modern architecture began with mathematics. Mathematical planning goes into creating almost every working, freestanding structure. From the smallest monument to the tallest buildings and bridges. For example, in order to build a structure, the area where the building will be erected must be measured to see if it will fit. Measurements and surveys, then the building plans need to be drawn up in scale drawings made proportionally smaller to the structure's real size. For more information, see below, and the amount of building material must be estimated, mathematics to figure out the budget. Finally, the actual structure must be built to specifications so the building will stand without collapsing. Geometry and measurement.
What are scale drawings?
Scale drawings are drawings or illustrations that are proportional in scale to the real structures they represent. In order for a new building to be designed, an architect must convert his or her ideas to drawings. But since the drawings can't be as large as the building, the architect uses scale drawings to depict the structure. These miniature versions of the actual structure show the sizes, shapes, and arrangements of rooms, along with structural parts, windows, doors, closets, and other important details of construction. The scale drawings of these buildings must be in exact proportion to the actual structure, with various scales used for this purpose. For example, 1/8 inch might be used to represent 1 foot, thus an 8-foot long building feature would be drawn as an inch long on paper. One of the most common scales used by architects is 1/4 inch equals 1 foot. These measurements can also be translated into the metric scale. Scale drawings are also used in other engineering fields, such as surveying. For example, distances measured in the field can be translated to a smaller scale, such as a drawing, in order to accurately depict what was measured. The ratio between the real distance and the drawn distance is called the drawing scale. If the measurement is 200 feet in the field and on paper the desired line is 8 inches long, then 8 inches on the paper would equal 200 feet on the ground, and 1 inch would be equal to 25 feet on the ground. This is translated as a diagram with a scale of 1 equals 25, 1 inch equals 25 feet. Or 125. There is another way of approaching such an illustration. If the longest distance measured in the field was 300 feet and the desired drawing scale is 1 inch equals 25 feet, then the minimum length of paper needed would be 12 inches, or 300/25.
What is an electronic calculator?
Most people nowadays are familiar with electronic calculators, small, battery-powered digital electronic devices that perform simple arithmetic operations and are limited to handling numerical data. Data are entered using a small keypad on the face of the calculator. The output, or result, is most commonly a single number on an LCD, liquid crystal display, or other display. It took a long time to go from the electronic motor-driven mechanical calculator to the electronic calculator. In 1961, the company Sumlock Comptometer of England introduced the Anita, a new inspiration to arithmetic, the first electronic calculator.
How has math been used historically in architecture?
Historically, there has been a great connection between architecture and mathematics. Ancient mathematicians were architects and vice versa, using their skills to build pyramids, temples, aqueducts, cathedrals, and a range of other architectural structures we find beautiful and awesome today. For example, in ancient Greece and Rome, architects were required to also be mathematicians. During medieval times, most buildings and structures carried some symbolic reference to the church. The mathematical end of architecture was almost forgotten during this time. By the European Renaissance around 1400, a new kind of architecture developed that emphasized mass and interior space to produce aesthetically pleasing pictures similar to those found in paintings and sculptures. This led to an entirely new way of looking at architecture and altered its connection to mathematics.
Has mathematics been used in art?
Yes, mathematics has been used in art either consciously or not over the centuries. Many of the fine arts deal with trying to comprehend the reality around us. And because both art and math try to explain reality using some concrete or abstract elements, it's easy to see the connection. For example, there are some obvious relationships between art, especially painting, and mathematics. An observer can use geometry to analyze a painting in terms of shapes, such as lines, points, circles, or other geometric shapes. Perspective can also be thought of as a mathematical quality of many realistic paintings, allowing the viewer to see reality, in the case of a painting, in 2 dimensions. And, in a way, Jackson Pollock's method of literally throwing paint on a canvas can be thought of in terms of fractal geometry. Mathematicians may work with quantifying and counting, but most of them will tell you that math is really more than a technical exercise and juggling numbers. Creativity is involved in discovering nuances in certain mathematics, with the mathematician creatively deciding what to concentrate on in order to solve certain complex problems. Just like a picture, mathematical concepts need to be created, invented, and discovered, much like the French painter Claude Monet, and others, invented Impressionism.
Why was Alan Turing so important to the development of computers?
Living in his native England during World War II, Alan Turing was instrumental in deciphering German messages encrypted by the Enigma cipher machine. Shortly after the war, he designed computers first for the British government. 1945 to 1948, then for the University of Manchester, 1948 to 1954. He also wrote several works on the field of artificial intelligence, a study in its infancy at the time, and developed the theory of the Turing test, in which a computer is tested to see if it is capable of human-like thought. Tragically, Turing, who is often considered the founder of computer science, committed suicide in 1954.
What was the Turing machine?
In 1937, while working at Cambridge University, English mathematician Alan Matheson Turing, 1912 to 1954, proposed the idea of a universal machine that could perform mathematical operations and solve equations. This machine would use a combination of symbolic logic, numerical analysis, electrical engineering, and a mechanical version of human thought processes. His idea became known as the Turing machine, a simple computer that performed one small, deterministic step at a time. It is often thought of as the precursor to the modern electronic digital computer, and its principles have been used for application in the study of artificial intelligence. the structure of languages, and pattern recognition. For more on Alan Turing, see History of Mathematics.
What were some of the first motor-driven calculating devices?
Many historians believe that the first motor-driven calculating machine was the Autorai, a device designed by Czechoslovakian inventor Alexander Rechnitzer in 1902. The next step occurred in 1907, when Samuel Jacob Hirsch Stark (1867 to 1937) produced a motor-driven version of his Thomas-based calculators in Vienna. In 1920, a prolific Spanish inventor named Leonardo Torres Quevedo (1852 to 1936) presented an electromechanical machine wired to a typewriter at the Paris Calculating Machine Exhibition. His invention performed addition, subtraction, multiplication, and division, and then used typewriters as input/output devices. Interestingly enough, even though the machine made a hit at the exhibition, it was never produced commercially. More and more such calculating devices with electric motors were invented. By the 1940s, the electric motor-driven mechanical calculator had become a common desktop tool in business, science, and engineering.
What are mathematical sculptures?
Mathematical sculptures are sculptures that represent some mathematical design. They are usually a geometrical figure and can be made of materials such as metal, wood, concrete, or stone shaped into squares, triangles, cylinders, specific curves, rectangles, spirals, and so on. Many of these sculptures represent different mathematical concepts, from polyhedral geometry and topological knots to fractal designs.
What is the Mozart effect?
The Mozart effect is a term coined in the 1950s by physician and researcher Alfred A. Tomatis, 1920 to 2001. It refers to the supposed increase in brain development that children under age 3 experience when they listen to music composed by Wolfgang Amadeus Mozart, 1756 to 1791. A more recent interpretation originated in 1993 from physicist Gordon Shaw and Francis Rauscher, a former concert cellist and expert on cognitive development. After a few dozen students listened to the first 10 minutes of Mozart's Sonata for two pianos in D major, K. 448, the researchers determined that the students experienced a short-term enhancement of their spatial temporal reasoning, based on a certain IQ test. But many other researchers claim that no one has ever been able to reproduce these results. Over the years, the Mozart effect has reached further into the public psyche. with highly debated claims of better health, memory improvement, and therapeutic uses of music, especially classical music. Proponents also claim the Mozart effect can be applied to learning such subjects as mathematics. They believe that exposure to certain types of music, especially classical music early in life, leads to higher future scores in spatial visualization, abstract reasoning, and sundry other mathematical concepts. But all these claims remain highly contested.
What famous structures were built using mathematics?
Actually, all famous structures needed mathematics. Especially in the initial phases of design and construction. Some of the more famous and exceptionally challenging buildings include the Chrysler Building in New York, a steel frame skyscraper built around 1930 that was the tallest building in the world before the Empire State Building. The Empire State Building in New York, a steel-framed, stone-clad commercial office skyscraper. Built in 1931 that rises 1,252 feet 381 meters high, the Eiffel Tower in Paris, France. Designed by architect Gustave Eiffel and built between 1887 and 1889 as a 985-foot 300-meter-tall exposition iron observation tower. And the Sears Tower in Chicago, built between 1974 to 1976, it is a steel frame with glass stroke. Tower standing at 1,450 feet 442 meters tall and is, to date, the tallest building in the United States. Places such as the Monterey Aquarium, built around 1980 with reinforced concrete and made compatible with surrounding waterfront structures, also needed mathematics in order to be constructed. Of course, when one gets down to it, all types of construction require some math knowledge for them to be built, even a modest piece of cabinetry.
In what way do some historians link mathematics to the pyramids?
The pyramids in Egypt were built as royal tombs for the pharaohs, first along the edges of cliffs as low rectangular structures called mastabas, then as tall, four-sided pyramids. The three structures most of us associate with pyramids were built at Giza, near Cairo, about 2500 BCE. The largest of these, the Great Pyramid of the Pharaoh Cheops, measures 481 feet, 147 meters, high. But there are no intricate pathways in this pyramid. It is merely a pile of limestone blocks weighing between 3 and 15 tons.
How did people in the Renaissance approach architecture?
During the Renaissance, not only mathematics but also architecture made great strides. In particular, church buildings were no longer based on the shape of the cross, but rather on the circle. This is because Renaissance architects believed that ancient mathematicians equated circles with geometric perfection. and that the circle must then represent the perfection of God.
What is computational sociology?
Computational sociology is a branch of sociology that uses computation to understand social phenomena. It takes great advantage of statistics to determine trends in data, and uses computer simulation in the construction of social theories. It is also referred to as the study of social complexity.
What is computational sociology?
Computational sociology is a branch of sociology that uses computation to understand social phenomena. It takes great advantage of statistics to determine trends in data, and uses computer simulation in the construction of social theories. It is also referred to as the study of social complexity.
What are some mathematical concepts used in demography?
Demography is the statistical study of human populations that reveals the characteristics of the population. This includes such factors as size, density, growth, distribution, and vital statistics. Some common demographic statistics include birth and death rates, life expectancy, and infant mortality rates. The birth rate, also called the crude birth rate, is usually represented in demography as the ratio of live births in an area population annually, most often expressed as the annual number of live births per 1,000 people, or a time division, such as at mid-year. Related to this is the infant mortality rate, which is the annual number of deaths of children less than 1 year old per 1,000 live births. The death rate, or crude death rate, refers to the ratio of deaths in an area population annually. It is often expressed as the annual number of deaths per 1,000 people. Life expectancy is related to death rate, and indicates the average lifespan of people within a certain population. It is calculated on the basis of statistical probabilities, usually represented by the average number of years a group of people born in the same year can be expected to live. If mortality at each age remains constant in the future.
What are some mathematical concepts used in demography?
Demography is the statistical study of human populations that reveals the characteristics of the population. This includes such factors as size, density, growth, distribution, and vital statistics. Some common demographic statistics include birth and death rates, life expectancy, and infant mortality rates. The birth rate, also called the crude birth rate, is usually represented in demography as the ratio of live births in an area population annually. most often expressed as the annual number of live births per 1,000 people, or a time division, such as at mid-year. Related to this is the infant mortality rate, which is the annual number of deaths of children less than 1 year old per 1,000 live births. The death rate, or crude death rate, refers to the ratio of deaths in an area population annually. It is often expressed as the annual number of deaths per 1,000 people. Life expectancy is related to death rate and indicates the average lifespan of people within a certain population. It is calculated on the basis of statistical probabilities, usually represented by the average number of years a group of people born in the same year can be expected to live. If mortality at each age remains constant in the future.
What is a population pyramid?
A population pyramid is actually two back-to-back bar graphs that show the distribution of a population by gender. One shows the number of males and the other shows the number of females. Most often in 5-year age groupings. These pyramids take a variety of shapes. For example, a triangular population distribution, also called a pyramid or exponential distribution, is usually indicative of a high birth and death rate, and a short life expectancy that is typical of less economically developed countries. A rectangular population distribution pyramid shows little change in size between the age groups. With more people reaching old age, this is typical of a more economically developed country. There are several uses for population pyramids. Besides calculating life expectancies, they are often used to find the number of dependents being supported in a specific population. Dependents in this case are considered to be children under 15, those attending school full-time and unable to work, and those over 65 years old or retired. Although this is a general definition and not applicable in all cases in all countries. Thus, governments can use such graphs to determine how much of the working population can support dependents. The graphs are also used to help predict future changes in terms of decades of a population's age structure. Historians use them, too, to find significant information based on past population pyramids.
What is a population pyramid?
A population pyramid is actually two back-to-back bar graphs that show the distribution of a population by gender. One shows the number of males and the other shows the number of females. Most often in 5-year age groupings. These pyramids take a variety of shapes. For example, a triangular population distribution, also called a pyramid or exponential distribution, is usually indicative of a high birth and death rate, and a short life expectancy that is typical of less economically developed countries. A rectangular population distribution pyramid shows little change in size between the age groups. With more people reaching old age, this is typical of a more economically developed country. There are several uses for population pyramids. Besides calculating life expectancies, they are often used to find the number of dependents being supported in a specific population. Dependents in this case are considered to be children under 15, those attending school full-time and unable to work, and those over 65 years old or retired. Although this is a general definition and not applicable in all cases in all countries. Thus, governments can use such graphs to determine how much of the working population can support dependents. The graphs are also used to help predict future changes in terms of decades of a population's age structure. Historians use them, too, to find significant information based on past population pyramids.
What are some of the statistical data gathered during the periodic United States Census?
Every 10 years, the U.S. government takes a census that gathers important statistical data about the entire population. In the 2000 census, this included place of residence, age, gender, race, ancestry, marital status, education, date of birth, place of birth, disabilities, work information, military service, language spoken at home, housing information, and school enrollment. Not all questions are repeated each census year. For example, 100% of the population was asked about their marital status in 1990, in 2000. It was only asked on a sample basis. According to the analysis of the 2000 U.S. information, on April 1, 2000, the population of the United States stood at 281,421,906.
What are some of the statistical data gathered during the periodic United States Census?
Every 10 years, the U.S. government takes a census that gathers important statistical data about the entire population. In the 2000 census, this included place of residence, age, gender, race, ancestry, marital status, education, date of birth, place of birth, disabilities, work information, military service, language spoken at home, housing information, and school enrollment. Not all questions are repeated each census year. For example, 100% of the population was asked about their marital status in 1990, in 2000. It was only asked on a sample basis. According to the analysis of the 2000 U.S. information, on April 1, 2000, the population of the United States stood at 281,421,906.